Okay, welcome back. Week 2. Any questions on the homework? Who's looked at it? Questions?
I have a question.
Sure.
About, let's see, I think it's number 3. And I guess I'm wondering if I have the correct starting point.
So question 3 is an ideal gas heated in 2 different piston cylinders. One of them is constant volume and the other one is constant pressure, meaning that the piston can move up and down. So let's set it up real quick so we can talk about it and we'll solve it all the way. So this is number 3. We have 2 devices. One of them has a little blocker on it, so this is volume is equal to constant. And the second one here, we have a device, and this can move up and down, so we have pressure is equal to constant. So, we're heating up the gas that's inside of this. This is an ideal gas. So we have a Q, rather we can do a Q dot or we can do a Q going into each of these 2 systems. And then the question is asking, how much does it take to heat the gas from T1 to T2? So this is all no numbers. Sorry, T1 not equals T2. T1 to T2. Right, so we want to know if we're heating up this gas from T1 to T2, how much heat does it take in each of these 2 devices? So what is our starting point for anything that looks like this type of a system? Energy balance. Let's write out the general energy balance, just so we get in the habit of it and we can simplify it. du dt is equal to summation of the mass flow rate times the enthalpies coming in for each individual stream or species. Anything else we could add on to here? The important thing though is we consider work to be shaft work. We have volume expansion work as well. Oftentimes we'll just write this as work, but we want to split it up into something that's like a turbine or an impeller versus one where the entire system is expanding. So let's simplify this one. What is the energy balance over a period of time going from state 1 to state 2? We don't care how long it takes. Right, but that's the cool thing about Thermo math is we can just integrate it and say state 1, state 2, and be done with it. So let's simplify this expression here, which is our general balance equation for the energy balance for this first volume equals constant piston cylinder device.
dV 0.
dV 0 and there is no flow.
Which, sorry, what's 0? So there's no flow. So this goes away.
And
And
no
all the
volume.
And the last thing is 0 2.
This one goes away. And is there shaft work?
No.
No, this goes away. So now give me the integral form.
Delta U equals.
Delta U is equal to Q. Whereas delta U is just the integrated du dt. The Q is just the integrated Q dot. Now, if you knew nothing about thermodynamics, and this was the very first thermo class you would have taken, we wouldn't necessarily know what to do with this, right? We're solving for Q, so we need to know what the delta U is, what the change in internal energy is. For an ideal gas, from previous knowledge, we know that what is delta U equal to?
MC delta T.
Yes, mCv delta T. Where this comes from is our goal for today and Wednesday, to do a rigorous derivation of where this actually comes from. Feel good about this one, right? Okay, what changes going to the constant pressure system?
Just have expansion terms.
This term doesn't go away, so we have to keep this included here, right? So if we do a quick little arithmetic,
Wouldn't that be plus because we are being in Q?
correct. My bad.
term when you integrate it just becomes enthalpy.
It does. So we can kind of do it a little bit funky here, more or less, but we can integrate this one, integrate this one, integrate this one. Delta U plus P delta V equals Q dot. And you can piece it together from there. So I basically solved the whole problem. But the key thing on this one here, which I really like this example, is don't fall into the trap of saying, oh, well, it's a closed system, so you do delta U. It's an open system, you do delta H. Right? It's not that case at all. The case with thermodynamics is you always start off with an energy balance, you always start off with an entropy balance, and then whatever the equations tell you, that's the truth. So that's the tricky part. A lot of times there's not a physical understanding of what's going on, or it takes a while to kind of work your way through the physical understanding, but always, always, always trust your math. Right? Thermo's kind of in that middle ground between something that's really intuitive, like heat transfer is a super intuitive discipline. Fluid mechanics, to some extent, is really intuitive, right? Because we see fluids flowing all the time. We know what hot is, we know what cold is. Versus something, let's say, like quantum mechanics, where there really is no physical understanding. You know, the wave function doesn't really have a good physical interpretation. Thermo sits in between those two, where you have to rely a little bit on the math, but you still have some intuitive sense about some of these different terms here. But enthalpy, for example, is something that's relatively abstract. Any other questions on the homework? Yeah?
How do you read this graph?
Ah, yes, yes, yes. Let's talk about the TS diagram. So, who has seen a TS diagram before? Like this. Who's seen a general engineering chart like a psychometric chart? Or some sort of a PV phase diagram? Right? So everyone's seen some type of an engineering drawing. The great thing with engineering drawings is that every one of them looks completely different, but they are all read in exactly the same way. So I'll reproduce the TS diagram here on the board. Okay, so the key features that we want to look at is we have entropy plotted on the x-axis, or the bottom axis. X, it's not necessarily it's funky, it's not a normal axis. Okay, entropy, which is in units of kilojoules per kilogram Kelvin, so according to our nomenclature, that would be like an entropy hat. On the y, or the vertical axis, we have the temperature in units of degrees Celsius. We have, the graph kind of looks something like this. Actually, let me choose a different marker. I can do this publicly. Marker goes up here and then kind of cuts off. I don't think there's anything fancy about how it cuts off. I think it's just because they didn't bother plotting it to a higher temperature than 800 degrees C. Okay. So these are the main features right here. Let's talk about this for just a moment. And then there's a bunch of other lines that are going on in between. If I want to follow a path, so if I know what the entropy and the temperature is of the fluid at a certain condition, how do I find it on this graph? Right, it's more or less just exactly like any other plot in a Cartesian coordinate system. I know the entropy, I know the temperature, and so then I would be right here. Pretty straightforward. Now if I wanted to go from this state, I'll call this state 1, and I wanted to isothermally change the entropy. How would I physically do that? What does that mean? How could I isothermally, well in the plot, that means I basically move somewhere along a horizontal line at constant temperature. Could someone give me an example of isothermally changing a system's entropy?
Volume expanding.
Bingo. Take a piston cylinder device right here, keep the temperature constant, expand it. By expanding it, you give the system more volume, you give the molecules more room to wiggle around. That would be an increase in the entropy. Likewise, if I wanted to keep the entropy constant and increase the temperature, I would follow up and down a vertical path. What's an example of keeping the entropy constant but heating it, or increasing the temperature? How do I accomplish that task?
Phase change.
No, not necessarily a phase change. You may be able to keep the entropy constant across the phase change. A simple example, though, would be pressurizing a system. Pressurizing and heating it or cooling it just right. But in a ideal reversible expansion, you follow a certain path on the PV phase diagram. You guys remember these things like polytropic processes, reversible expansions, where you have these expressions where it's like P2 over P1 raised to some power? That's following a path of constant entropy. And we'll talk about how we get these expressions basically over the next couple lectures. So, not scary at all, right? Now the tricky part on the diagram comes when we add in all of the other fun lines. So I'm trying to look at this one here. So we have lines of constant, let's see, where's the constant pressure lines? Ah, here they are. The constant pressure lines look like this. Okay. We also have a phase boundary hidden in there. They don't tell you it's a phase boundary, but we know it's a phase boundary because it looks kind of like all the other ones that we've seen in engineering diagrams. Okay, so these are lines of constant pressure. The idea is exactly the same. We run parallel or perpendicular to the axis here. So if we follow a line here of constant temperature, we're choosing an isothermal path. We follow a line of constant pressure, we're following an isobaric path. Why is the line flat here? What's going on in this archway?
We can
Change
pressure
in
liquid.
phase.
Right, during a phase change, which two properties are constant?
Pressure.
Pressure and temperature. We're going to derive why that's the case in this class as well. What is this point right here?
Critical.
Critical point. Above this temperature, we no longer have a liquid phase that can exist. We only have a supercritical fluid. So if I wanted to create a liquid without having to necessarily go through all of these saturation points, I could take it, go supercritical, come in here, and then condense it back here on the liquid side or something like that. So sometimes that's a convenient way to do liquid phase transitions. And then there's also a bunch of other lines. So I think there's a constant enthalpy line. The constant enthalpy lines look like this, I think. Something like that. But more or less, how we read these diagrams is all we need is two pieces of information. So these are constant enthalpy lines. I'll call these H hat. I think if I'm reading that correct. So if I have two pieces of information, if I have the enthalpy and the pressure, right, I could fix myself here. I could read at which temperature that point occurs at. I could reach at which entropy this occurs at. Inside of this two-phase region, there's lines of constant quality. Here goes constant quality. They're like kind of like this. This would be like 10%, this would be 20%, this would be 30%. That's the fraction of vapor in the system. So all I need to do in any engineering diagram, whether or not it's a TS, an HS, a PT, a PV, whatever the case is, I'm going to be throwing at you guys engineering diagrams on quizzes, on exams, and I'm never going to have to be talking about them. But the idea is, if you can read one that's complicated, you should be able to read all of them. Because with thermodynamics, all you need to define is two intrinsic variables. And with two intrinsic variables and a relationship, you can determine all the other properties of matter. So this chart right here, you define two variables: pressure, temperature, enthalpy, quality. If I tell you it's a saturated steam at a particular temperature or at a particular entropy, that'll fix you out somewhere on this line over here. If you're a saturated liquid, you'd be somewhere over there. And with those two variables, you can read all of the other properties off. So regardless of what type of diagram it is, we can figure it out. Now, for the rest of this question on the Rankine cycle here, I'm not going to go over the Rankine cycle at all. But for every single process in the Rankine cycle, if you look at the diagram right here, right, we've got a boiler, a pump, a condenser, a turbine. Your goal is going to be to perform an energy balance on every single one of those cycles, potentially even an entropy balance on every single one of those. And from that, figure out Where am I starting? Where am I going? Where are the dots at for every single one of the streams? So all you need is data tables to perform like your material property balances, and energy balances basically to figure out which pathways you're going to go across there. But it's nothing more than a series of energy balances and entry balances. More questions, homework. So I do rely on people asking questions for the homework because in class we do very limited number crunching. Homework is almost exclusively number crunching. So to fill that gap in between me not doing examples in class and the homework being sort of somewhat tenable or something that you can easily handle, I kind of expect some questions throughout. So that way we can kind of tailor our examples based on that. Okay, homework is due 1 week from Wednesday. Next Monday is the holiday, so there's not going to be any class. So Friday will be the last in-class time. If you haven't already filled it out, fill out that survey for the office hours. I'll take a look at it today after class, and we'll get the office hours assigned so that we can do more one-on-one specific help. Because oftentimes it's difficult for me to go really into detail about a particular challenge that you might be having with the homework. So I can do general questions like this to give everyone a jump start, but for specific troubleshooting, we'll have to do one-on-one. Okay. So, what our goal is, as you remember, the three primary variables of the universe from the perspective of classical thermodynamics, right? The way that we kind of look at the universe. We have only three variables. Well, four if you include mass, but if we look at a sort of intrinsic variables, we have the internal energy per unit mole. I guess it's kind of think of this as the energy density. You can think of this as the entropy density, and this would be the mass density. If we wanted to do this for an open system, the universe is not open, by the way, right? The universe has, we can lasso one, we can't really physically, but if we think about the universe as not really exchanging any information or mass with other universes, right? We can think of it, the whole system as a closed system. More locally, if we have a system that is open, which again is not the case, we can have U, S, V, and then mass. Right? Those would be the four primary variables. For our purposes, we're actually going to consider most everything that we do a closed system. When we do balances for the Rankine cycle or for piston cylinders or whatever the case is, right, we'll be tinkering around with energy balances and entry balances. But for the most part, what we're going to be really interested in is phase change processes. So when we have a phase change process, right, let's say it's a liquid-vapor equilibrium where I have liquid on the bottom and vapor on top. The way that we're going to be performing most all of our calculations is we're going to assume that this liquid is an infinite ocean and this vapor is an infinite vapor. We're going to use that information to calculate the properties of the liquid phase, calculate the properties of the vapor phase, determine what's the total amount of vapor, what's the total amount of liquid. Then use that information to plug it into design equations for a distillation column or design equations for a heat exchanger. So calculating the material properties is really the difficult part. From this homework assignment, from only a couple of classes, we can basically go through and do a whole bunch of balances. So for the actual mass flow rates in and all that kind of stuff, that's not too bad. If we have data tables like the TS diagram, it's really a trivial exercise once you figure out how to do the energy balances really efficiently. Tricky part is coming up with the relationships to predict U, S, H, G, and then ultimately use that information to predict phase changes. So what we need though is I don't have a trivial way to go in the lab and measure these variables. Density, yeah, that one's pretty straightforward. In an industrial process, it's still kind of a pain. It would be much easier if we could just measure pressure and temperature. So what we need to do is we need to convert the variables that all of thermodynamics is founded upon into variables that we can actually design equipment into in the laboratory. For example, how do we know that the internal energy is related to C sub V, the specific heat at constant volume? How do we know that the enthalpy is related to the specific heat? So we're going to be talking about how we get to that structure of the system. So to start it off, what we're going to do is we're going to derive sort of one big master equation, which is the combined first and second law. So what we're going to do is we're going to have a system, an open system, where we have a mass flow rate stream in, where we have work and heat entering the system. We're going to keep temperature and pressure constant, which means we can potentially have PV expansion work through the system as well. Imagine this is some sort of a balloon, or it's got a movable part. So the mass balance of this system, right? The box is our system. The mass balance is we're trying to keep track of how much mass is entering or how much mass is leaving. So the rate of change of the total mass of the system as a function of time is just going to be equal to the rate at which mass enters the system. Very trivial balance. The energy balance, I'm going to ultimately substitute the mass balance into here to speed things up. The total energy of the system, how it changes as a function of time. All we have to do is keep track of all of these sources of energy in, all of the sources of energy out. We're doing a differential form, so we're doing this over some unit of time. We have the mass flow rate times by the enthalpy, but I'm just going to substitute in dm dt. dm dt times by the specific enthalpy of that stream coming in. We have the rate of heat entering the system. We have the loss of energy if it expands, or the gaining of energy if the system contracts, right? Because this mass flow rate you could think of as being negative too. You could have mass leaving the system. And we have potentially some shaft work going on. Turbine, impeller, something going on in the system. Let's do our entropy balance. Same general idea. The rate of change of the entropy of the system as a function of time, this is the differential form of the entropy balance, is going to be equal to the mass, change in mass flow rate going into the system times by the specific entropy. We have entropy being transferred into the system in the form of heat, and we potentially have entropy generation going on in the system. So to make this process a little bit more streamlined, we're just going to say over some time dt. So we don't have to write that dt. We're going to rearrange this expression a little bit. T ds is equal to dm ts hat plus q dot plus ts dot. Okay. Let me write this a different way. This is not conventional now. Ts hat dm with the differential at the end. So what we're going to do is we are going to take the second law and substitute it into the first law, because they both have heat. So if we rearrange this, Q from the entropy balance is equal to T ds minus T s. Substituted into our energy balance. So what we're going to do is we're going to take the second law, and substitute it into the first law. of this expression is here. The purpose of what we're doing right here is to help us calculate property changes in entropy and internal energy. Those are all state functions. So ultimately, we don't care about how we go from point A to point B. So to simplify our lives, what we're going to say is in all of our mathematical calculations, we're going to focus on idealized systems. To make it easier on ourselves, we're going to say that the entropy generation is 0, meaning that we have chosen a path that is not going to be generating entropy when we calculate these state changes. And we're also going to make it easy on ourselves and say that we're not going to be adding or subtracting work to the system. Again, no reason to overcomplicate our lives. So with that, we get rid of this term, we get rid of this term, and we'll do a little bit of rearranging here. So du is equal to t ds, so let's check that one off, we got that one taken care of, minus p dv, check that one off, and then we'll combine these two, plus h hat minus ts dm. What is this equal to right here? G. This is g hat, there we go. So our combined first and second law, for an open system we have derived du might equals t ds minus. And this is going to be our starting point for what we're going to be talking about for the next couple of days. Or for a closed system, this is for an open system. For a closed system, we can simplify it down. We generally write this intrinsically. Okay, that's for the closed system. Combine first and second law. And for those of you who still have your handout here, we're going to basically be deriving a lot of these expressions. That's our goal. And you'll see, I don't know if you guys have your sheet in front of you, right? It says thermodynamic functions. du is equal to TdS minus PdV. What this expression is here is the combined first law and second law of thermodynamics. So basically this is a doubly safe law, right? All of thermo is contained within this one relationship. And what we talked about hypothetically saying, what if we had one relationship that relates between the three fundamental variables of the universe? V, S, and U. Density, entropy density, energy density. This is that expression that we have derived. The bummer part about this expression is it is not in units that are at all useful for us. That's not in our control, right? That's just how thermo is formulated. These are the laws of the universe that thermodynamics is built upon. The first law is basically law of conservation of energy. Second law is the second law. It's kind of its own deal. And we live in the universe that has volume and real space. So these are the relationships. So if you also look at this handout that I printed out, you'll see that this is also equal to CV dt plus a big, long, fancy expression. This is what we're going to do right now. We're going to show where this comes from. How do we get this expression? Because what this equation tells us is that instead of us having to design an experiment where we have to keep the entropy constant across the experiment, that's not trivial, right? If I go to a water bath in the laboratory, I dial in what temperature I want to perform the experiment at. I don't dial in the entropy that I want to perform the experiment. So what we need to do is we need to find a way to calculate changes in internal energy, either so if we have an equation we can evaluate the equation, or we can find a way to tabulate the data in a more compact form. So what we need to do then is to get rid of this expression here and find out how to convert ds into something like dt or dp, for example. This expression right here we don't often see, because if you were to plug in the ideal gas law, this would go to 0. So for an ideal gas, the internal energy is only a function of the temperature. It's because this more complex term goes away. And in general, this expression is only really important when you get to higher pressures, or you get to conditions that are close to when the fluid is going to condense. But when you're at very low pressures, this expression here is pretty insignificant. And the same thing holds true for the enthalpy. You see you have a slightly different expression on your equation sheet, and you've also got terms for A and G as well. Okay, so what we need to do before we can go on is we need to do a little bit of a recap of some calculus properties. It's in the way. Okay. Chain rule of differentiation. So, what we can use this expression, or this relationship for, is let's take any function, in this case we'll just say it's du for the sake of simplicity. We want to know how is the rate of change of the internal energy of the system changing as a function of whatever we care about. So how we accomplish this is the total amount of change as a result of the internal energy. But the internal energy can change from a number of different things. It can change as a function of entropy. It can change as a function of the density of the system. But it's only two variables. So in thermodynamics, the mathematics becomes relatively simple because there's a limited number of variables that can control how processes change. So what we do is we'll say here, we're going to expand du with respect to, right? We want to monitor how du changes as a function of this case of, let's say, v and t. So what we're going to do is we're going to say that du dt at constant v dt is we're going to monitor how much of the change is coming from the contribution of changes in temperature, plus how much is going to change based on the contributions to changes in the volume. So for example, we could think of this like, what is the rate of change in the balance of your bank account? This could be the rate of change of how much your salary is getting paid, and this could be the rate of change of how much you're spending extra money. So in real life, we have multiple different contributions. This could be how much you're spending at Cafe Rio versus Taco Bell versus on airplane tickets versus gas money. In thermodynamics, we don't have as many variables, so we only have to expand it with 2 variables for a closed system, 3 variables for an open system. So we can do this with any thermodynamic function and expand it with respect to any other thermodynamics function. So we could expand enthalpy with respect to U and S. We could expand Gibbs free energy with respect to V and T. Right? So any thermal variable we can expand for any other one. So this is a general rule. So don't think of it only as these functions here. It's just any x, y, z function that we want. We write these little subscripts here to remind us the variables that we're holding constant in our system, or the variables that we're changing. But in a true partial derivative, all the other variables are held constant. But since there's a finite number that we're going to keep track of, this is just sort of for convenience to remind us of how we started this calculation. Right? We're changing v and t. For this process here, we're changing t, holding v constant. This process here, we're changing v, holding the temperature constant. For Thermo, the functions are well behaved. So Thermo functions are what they call well behaved. What that means is there's not any weird discontinuities or zeros largely, and there's some exceptions, but for the most part, what that tells us that we can do is if we have any arbitrary differential, this is effectively equal to, we can take the reciprocal of it. Right, so this kind of means that we can cross multiply terms in our differential, or we can cross them out. And the order of the differentiation doesn't matter. Oops. So what you can see here is I've swapped out the order that I've taken these partial derivatives. So I'm looking at what is the change of x as a function of y, then as a function of z. That's the same thing as the change in x as a function of z, and then as a function of y. So the order that you take the partial derivatives doesn't matter. It's triple product rule. From the chain rule, we can derive the triple product rule. I won't, I'll just write it out. So this one's always a tricky one to remember. But the main thing is for any three variables, right? Again, we're dealing with thermodynamics. There's three variables of the universe. That's all we ever have to keep track of. You just kind of do a rotation. So if I have, let me get a color marker out here. You just swap out the positions. This goes there, this goes there, this goes there. You do that 2 more times. So dx dy at constant z times dz dx at constant y times dy dz at constant x is equal to -1. That's the triple product rule. And this one's also called the chain rule. I double checked my notes in the sampler book. That's what they like to call this one as well. I guess this is the chain rule of differentiation. This is just the chain rule. This basically shows that you can cancel or expand partials. So in this case here, if you just cross off the dy in the numerator and the dy in the denominator, you can simplify your expression. So you can either expand differentials or you can shrink them down depending on the particular needs, but that's the chain rule. Those are the major ones. There's a few other rules listed in the Sander book, but these are the major ones that we'll need to go through our derivations. Okay. So let's apply these things. See if we can learn something about thermodynamics. So what we're going to do, let's see, I still have, okay, closed system, that's what I want to keep. So one thing to remember with these derivations is that they are, to some extent, we already know the answer of what the useful equations are. So we only show the derivations of the useful equations, but there's a lot of other stuff that you can derive. That's true, but not particularly useful. So for example, what we're going to say is we're going to expand. So we'll start off with the first and second law. Yeah. And what we're going to do is we are going to expand, also we have du equal. So the first thing that we can do is we can start to rearrange this expression here. So here we have our starting point. This helps us to understand du. We could rearrange this and solve for the changed entropy. Rearrange the expression, so then we have du over t plus p dv. Oh, we can also add in here if we wanted to plus g. Yeah, I changed this up a little bit. See, this is g as a function of per mole times by the molar flow rates as well. And then this one here would be and for an open system to keep it general.
Do you need another T under P?
Let's see. Yes, you are correct. I need that here. And now we have an expression for changing entropy. We'll do the same thing for enthalpy. So with enthalpy though, however, we have enthalpy that is defined as U plus PV, or for a intrinsic system, we can write it like this. So if we want to figure out what the rate of change in enthalpy is, we need to take the derivative then of this expression, in which case we're going to use the, I believe it's called the product rule. This is going to be P dV plus P. Substitute in our differential change of internal energy into our expression down here, and we can derive a relationship for H . This is for a closed system. So you'll see we're highlighting some of the key differences between internal energy and enthalpy. Internal energy, its native variables are entropy and specific volume. The native variables of enthalpy are entropy and pressure. We can repeat the same process for Helmholtz and Gibbs. So for example, for the Helmholtz energy, A is defined as U minus TS. So in that case, dA is equal to du minus TS. Should make it specific there. Again, we're going to substitute in the combined first and second law into the definition of the Helmholtz energy. This is all we're doing right now. This is the definition of the Helmholtz. And we're just being diligent with our mathematics, and we're expanding everything with the product rule, because everything's a function of everything in Thermo. So you say, take this expression, substitute it into here. We cancel things out, and what we get is dA. The Helmholtz energy is a native function of temperature and volume, which is very convenient. And we repeat the process again with the Gibbs. Gibbs free energy is defined as enthalpy minus temperature times entropy. And if we substitute everything in together again, this is just the definition of the Gibbs free energy. So we don't know why we define the Gibbs free energy this way, but it's just very, very convenient. And the reason why it's very convenient is because when we go through all this mathematics, we find out that the Gibbs free energy's native variables are temperature and pressure, which makes it really nice for us. But these are all for a closed system, not an open system, which is predominantly what we're going to be worried about. These two are for open, but for the rest, I just made it simple so we can get through the material. So Gibbs free energy is a function of changes in pressure and temperature in a compact form. That's not to say that the Gibbs free energy is not a function of entropy or enthalpy or internal energy. It is. But the math works out the simplest if we look at changes in Gibbs as a function of pressure and temperature. But the key thing to remember is that everything is a function of everything else in thermodynamics. Right? There's always going to be, so if you change any thermodynamic property, no matter how small you think that change is, it is changing all of the other properties unless you choose a very specific path. Let's see, a constant temperature path, a constant pressure path, a constant entropy path. So what we use these expressions for, and just as a reminder, these primary expressions where we have a relationship for du, we have a relationship for the change in entropy, we have a relationship for the change in enthalpy, we have a relationship for the change in Helmholtz, and same thing for Gibbs. All we've done is we've used the combined first and second law of thermodynamics, defined different functions. We defined Helmholtz, we defined Gibbs, we defined enthalpy. All of these functions are only functions of other state functions. So they are state functions themselves. And then we were just diligent with our mathematics by expanding out the product of two thermodynamic functions, right, where we kept track of the changes of both. That's just the product rule of calculus. And then rearranged them and simplified them. So every single one of these expressions is an exact representation of the first law, law of conservation of energy, and the second law of thermodynamics. That's all we've done so far. They look a lot different because we've made up variables along the way. Right? Pressure and temperature, those are made up variables. But we've made them up because they're very useful. Now where things really start to open up is how we now relate between these different functions. And how we accomplish that is by combining these general rules of calculus and differentiation with the combined first and second law of thermodynamics. Every single one of these is a representation of the first law and second law of thermodynamics. All we're doing is making sure we're not losing energy or losing entropy. That's all of these expressions mean. So what we'll do is we will expand u with respect to, in this case we'll expand it with respect to S and V. So we'll use our chain rule of differentiation. I'll just reproduce it over here. du is equal to change of this versus temperature at constant volume. This is not what I wanted to do. I wanted to expand it with respect to S and V. That's a different expression, sorry. So expanding with respect to S at constant V, ds. So this is just a completely general relationship. The only thing that's important here to remember is that we are expanding our thermodynamic variables with respect to two other thermodynamic variables. That's just based on the Gibbs phase rule, or the fact that we have three variables that define the universe. Now, it just so happens that that expression looks real close to this one here. All right, so I'll reproduce the combined first and second law. du is equal to d. So now we can generate what they call a thermodynamic identity. T is equal to d. And pressure, negative pressure, is equal to du. We can derive several more of these identities by basically following exactly the same procedure that we did here. We have the combined first and second law. U is a function of entropy and volume, so we just expanded it with respect to entropy and volume, and we came up with two identities. This temperature is equal to this, negative pressure is equal to that. We could follow exactly the same procedure for all these other different equations. Expand enthalpy with respect to entropy and pressure, expand Gibbs with respect to pressure and temperature, and you'll see on your sheet you have thermodynamic identities. Those are how all of those functions are defined. These are new relationships that we have to relate between different thermodynamic properties. So one last thing very quickly, apologies on going over for just a few moments, but it is how we derive the Maxwell relations. Now, Maxwell relations they always are a little bit tricky. So we're going to take these two identities here, and we're going to rely on, the relationship I just erased, that the order of differentiation doesn't matter. So I'm going to take these two identities here, and I'm going to play around with the partial derivatives a little bit. So this one here is du ds, this one's du dv. I'm going to basically kind of swap out the order of these. So what I'm going to do is I'm going to say the partial with respect to v at constant entropy of, and I'm going to do the opposite these two expressions are 100% equivalent, right? All I've done is swapped the order that I've taken the partial derivative, which is totally allowed in our well-behaved thermodynamic functions. Now, we were clever about this derivation, so it just so turns out that both of these expressions are thermodynamic identities. So du ds at constant V is just equal to the temperature. Du dV at constant S is equal to the negative pressure. So then I can write here that this is d dV at constant S of the temperature. This is d ds at constant, scribble that a bit too much, constant V of negative pressure. Then I just set these two relationships equal to one another. And this is what they call a Maxwell relation. And if you look at the handout sheet, you have 4 additional Maxwell relations. Now, how are we going to use these? It all comes into how do we develop basically this expression here. This is ultimately our goal. Let's use the answer of those examples. This is one of the equations on your equation sheet. Right, this is just the combined first and second law of thermodynamics, basically what we derived over there. And what we'll be deriving in class on Wednesday is this expression here. what we've accomplished in going from this expression here to this one is this is actually an equation that we can use to calculate changes in enthalpy. All we need to have access to is the heat capacity of the material and how it changes as a function of temperature, right? Because then we could just envision integrating this from T1 to T2, right? And that allows us to calculate where delta H is equal to the integral of the differential change in enthalpy, right? So all we need to do to calculate enthalpy changes, which we know are really important for doing energy balances, like in the homework assignment, if you don't have a table with all of them, we need to calculate it somehow. So with this equation, we now know that if we have the heat capacity of the material, we just need to integrate it over temperature, and then we've got this big mess right here. But this is why we care so much about equations of state. Right? An equation of state relates between the specific volume, the temperature, and pressure of a fluid. This gives us what we call an equation of state, EOS. Can someone give me an example of an equation of state? Ideal gas law. What's another one? Van der Waals. What's that one?
Van der Waals.
Van der Waals. What's some other ones? Virial.
Cubic equation of state.
Cubic is a class. We've got Peng-Robinson, SRK. I don't know where the S, R, and K are. Most people use an equation of state to say, oh, well, what's the pressure of this tank under these sets of conditions? That is the most rudimentary, basic use of an equation of state. And it is one that we care very, very little about. But the ability to accurately predict how the pressure changes with the volume allows the equation of state to help us calculate the enthalpy, help us calculate the Gibbs free energy. If we can calculate the Gibbs free energy, we can calculate phase changes. So an equation of state is so much more than just what's the pressure in this tank of gas. An equation of state, an accurate equation of state allows us to calculate 100% of all properties of a system. So if you can accurately predict how pressure, temperature, and volume relate of a particular fluid, you can calculate how much energy it takes to do different things. Right? So the equation of state is very powerful. So that even though this looks like a junky mess, it's honestly the best we can do with Thermo. But if we have an expression that relates between pressure, temperature, and volume, everything contained within this bracket is just an equation of state. So all we need is an equation of state, and we integrate it with respect to pressure, and that tells us how the enthalpy changes. So we're going to need thermo identities. We're going to need Maxwell relationships in order to take this combined first and second law that we can't use and turn it into a form that we can use. All right. Thank you, guys.